This is from 2.1 Problems, the third page on the second sheet. So some introductory concepts. You need to know the supersoluble ions, most of which are positive. They are at the top of the solubility chart. They think you know those. It is not going to be stated or even hinted at. They just think you know. Included in there is sodium and potassium. So when they say potassium permanganate, is it reacting, right? Then people say, well, where's the potassium? Well, this is the permanganate because these are the three reactants, and it's certainly not that or that. So this is the permanganate. You're not exactly expected to know that, but by all logic, that's it. Where's the potassium? Well, as I say, potassium and sodium, which will come up later, are supersolubles, and when you put them into water, an acidified solution of sodium chloride, and notice that everything's aqueous, aqueous, aqueous. So on here, I know that's, well, those aren't, but all the reactions are aqueous, so it's in water. They don't have to say it's in water, they said it with the aqueous. Then the potassium lets go of the permanganate, and it just runs away. And it's a supersoluble, so it has no intention of combining with anything else in water. So what you get is potassium over here, and then potassium over here, both aqueous, both +1, and it's not going to do anything, and so it remains the same. It's the same on the left, it's the same on the right, and this is the net ionic equation, so it cancels out because it doesn't, in effect, do anything. The same thing goes for the sodium in the sodium chloride. The sodium lets go of the chlorines, it remains soluble, dissolved, and that's true on the right, and so it cancels out in the net ionic equation. If you don't remember what that means, go use that phrase into YouTube or ask me. So the first thing that we have to do is find the Cl minus moles. Now we can do that by finding the NaCl moles, but you said the Na doesn't count. Well, it doesn't count for the reaction in this way because it doesn't actually do anything. But we find the moles of Cl by finding the moles of the NaCl because this is liters, essentially. Move the decimal 3 spots smaller. And this is the molarity, and they totally think you know and remember. If we will take the liters times the molarity, moles per 1 liter, then we get moles. I know they wrote it this way. That's just so they can use the milliliters. I think that is coming up with one more method to do things instead of sticking to something that works. We just take liters times molarity and get moles. So if we had 10 NaCls, we could think of it one of 3 ways. We have 10 groups of NaCl. We're going to get 10 Na pluses coming off, and we're going to get 10 Cl minuses coming off. It's kind of like if you have the church marriage retreat and you have 30 couples. You have 30 couples or 30 husbands or 30 wives. You can look at it one of 3 ways. It doesn't really matter which way you do it. You get kind of the same concept in either way you look at it. So when I find the moles of NaCl, I have also found the moles of the Cl minus. Calculate the volume of the Cl2 gas in the sealed container. And it's very important that we know this, and it's the gas. So volume of a gas is governed by PV equals nRT. They told us the pressure, back up here, there. They told us the temperature, except add 273 to make it Kelvin. There's the Kelvin. You got to know the constant. Well, you don't technically have to know the constant. It is supplied in the information pages at the front of the test, but it would be nice if you knew that, but you know, it's not going to come up that often, so it's not that big a deal. But for atmospheres, the constant is 0.0821, or it's 0.06. Okay, well, you're going to get close enough with this, believe me. You want to argue about the 5th decimal of this? Ridiculous. And the unknown is V, so we're going to solve for V, and so they pre-solved for V. And the trick to this, and there is a bit of a trick, but it is logical, is that the moles of the Cl2 is not the moles that we just found. Observe. For every 4 Cl minuses given in the reaction, only 2 Cl2 gas molecules are created. If you put in 4, you get out 2. In other words, this number will be half of whatever that is. This number of gas will be half of whatever the moles of Cl minus was. The ratio is you'll get 2 for every 4. Well, that's half, and if you put times a half, I'm sure you'll get away with it in the context of this whole thing. But to be technical, they are more correct, I suppose, that they canceled out their moles of Cl minus and generated moles of Cl2 with 2 to 4, but it doesn't super matter. This then is the moles, and that goes in for N. It's the moles of the gaseous Cl2 molecules. Solve for V, and you're done. Oh, technically, there are all these units on the constant, but I can't imagine that that is the problem here. So they did a reaction rate test on this reaction system, and here's their data. Determine the order of the reaction with respect to each. So Cl minus they want first, so let's find a way to lock down where Cl minus changes and nothing else does. Well, H plus doesn't change in any of these, so we can ignore that. For the purposes of getting the exponent on our molarities, we can ignore this. Again, they wrote this out in this incredibly long-winded way. But notice all this is going to cancel out. K is going to cancel out. And they're now, once I cancel that out, doing what I said. And notice I'm going to get the same answer. I'm just jumping to this. Writing all this is a complete waste of time in the real test. Many people don't finish. Writing all this out does not get you any bonus points. There is no such thing as a bonus point. So talk about a waste of time. So let's nail this down and let's get Cl minus where it changes and nothing else does. Well, we can do that by going from trial 1 to trial 2. Going from here to there is a multiple of 3. So the way I've been writing it is then 3 to the unknown power equals, and then what rate does what does the rate increase by? Now we went from here to there, and you do get a calculator, and honestly, I had to get a calculator. And you can divide this by that. Now I know it's tempting to go, this is the top and that's the bottom, but remember, when we said this multiplied by a factor of 3 to get here, effectively what we were doing is saying this divided by that is 3. So we had to go the same direction. This divided by that is really close to 9. Just call it 9. Remember, these are all experiments and there are presumably tiny bits of error in the measurements. So what we get is that, which is that. I'm just agreeing with them. Therefore, the exponent on Cl minus is 2. X equals 2. Determine the order of reaction. Determine the order of reaction. State second order with respect to Cl minus. Write that in. You really might miss the point because they said it really clearly. I don't know why that's so important, but to be fair, that is in the directions. So let's nail down MnO4. So does this change where nothing else does? This changes and that one doesn't. So we can go from 3 to 1. How about that? We'll say this doubled from 3 to 2. Trial 3 to trial 2. This did not change. And then this doubled, or really close. Remember, they're not using enough sig figs to really show that. Really close. So what we have in my version then is the molarity doubled, that is to an unknown exponent, and the rate also doubled, and the exponent is 1, which is essentially what they just said here. And don't forget, reaction is first order. Write it in with respect to MnO4 minus. Then comes one of those things that I have trouble doing. It's called read all the directions. The reaction is known to be third order with respect to H. Using this information and your answers, write out the rate law. And when I was doing this in tutoring, I forgot the H for a moment because I was so able to disregard it before, I forgot it mattered. It is known to be third order. Read all the words, kids. So rate will be K times Cl minus to the power discovered, MnO4 minus to the power discovered, and they told you H plus is third order, the exponent is 3. Discover K, right? Calculate K. You can pick any line. They picked 104, that only appears here. They picked line 1. So put this in, but we know the power is 2. Put this in, but we know the power is 1. Put this in, and we know the power is 3. This is the power of 2, power of 1, power of 3. This is the rate. And that all solves for k because watch what we're doing. We're taking this, this, and this and dividing under the rate. Well, the other direction, but it doesn't matter. So these three, with the proper numbers, I guess from trial 1, if you like to, if you want to follow them, end up under rate. And don't forget to take the powers to the second power to the third power, and then times that, and then divide into that, and we get this. And if you don't put the units, I really bet you missed the point. That would be a shame. Numbers do not count without units, and I have to agree with them. You got to put the units. It's a big boy and girl test. It's a college level test, and you have to have the units, and they have to be correct. So how do we get the units for that? Well, what we have here in the rate is molarity per second, and they told you that up here, or yeah, I suppose that's the only place it's actually stated. It's in molarity per second. S to the minus 1 means that the S is below the molarity. This is now molarity to the 6th, so we get molarity per second over molarity to the 6th. This then can be solved, if you like, this way, because that's a fraction if we want, right? How do you divide by a fraction? We multiply by the reciprocal, so instead of doing that, let's do this. And this cancels out one of those, and we get 1 over molarity to the 5th times seconds. Molarity to the 5th times seconds. And the molarity in the bottom of the unit for k should be 1 fewer molarity than whatever the total number of molarities was, the powers, total powers for molarity was in the rate law. Because we said, look, it's going to be 2, 3, 6, and you need to cancel out all but one of them. So what you're going to do is have molarity to this number of exponents minus 1, you're going to have molarity to the 5th times seconds. Is it likely that the reaction recurs in a single elementary step? Now, I actually forgot what they meant by that for a moment myself, but what they mean is, if you have a reaction that you know for a fact happens in one step and it does not need to create this, which creates that, which creates that kind of thing, if that's true, then what you can do is you can leap right ahead and you can determine the rate law from the reaction. Let's just pretend that this is one step. It's clearly not, but let's pretend. If it was one elementary step, then you could say the rate law will be rate equals k times h plus to the 8th, cl minus to the 4th, MnO4 minus to the 1st. But you can't tell by looking at the reaction if that's true. It almost never is. And in fact, when we did the actual experiment, instead of just guessing, and we did a data table, we found out that the rate law is not following that pattern. It is not Cl minus to the 4th, MnO4 to, well, that one matches out of weirdness, but this would have been an 8 if you look up top at the coefficient in front of H+. So does the rate law match the coefficients in the balanced equation for the stoichiometry, as they said in the answer at the bottom? No, it does not. That means that this is not an elementary single step reaction. Reaction does not occur in one elementary step because the rate law does not match or have the exponents agreeing with the stoichiometry. Are, I personally probably would have said the balanced reaction, the balanced overall reaction, or to put it another way that I'm sure they would have to admit is a justifiable version, the rate law exponents do not match the coefficients in the balanced reaction. So this is not one elementary step.